So we're in the middle of doing two examples. So I did this example. I'm going to show that f of x equals 1 over x is continuous at 0, 1 on a whole bunch of these points 1 over n. I'm only looking at certain points. And basically what I found out is that at 1 over n, I need delta to equal the min. I have it set up 1 over 2n, comma, epsilon over 2n squared. Which means that at 1/2, I have to be between, delta has to be between a minimum of 1/4 and epsilon over 8. So basically I get, this might be like epsilon over 8, because if epsilon's really small, then epsilon over 8 is going to be smaller. At 1/3, I get epsilon over 18, which is quite a bit smaller. At 1/4, I get epsilon over 32, which is quite a bit smaller. And at 100, I get something ridiculously small. So I start with a big interval, smaller, smaller, smaller. Now let's go to this next example here. Now I'm looking at x squared on 0, 1. That's supposed to be the function x squared. And I'm going to do the same thing. And to do this, what I can do is I can just say, well, I need x squared minus, I'm testing the continuity at the points like 1 over n, so I need that this thing is less than epsilon when x minus 1 over n is less than delta. Well, let's take a look at this guy. That's equal to x plus 1 over n times x minus 1 over n. And that's good because that's my delta statement, basically. But I need to figure out a bound for this. Well, the biggest value x could possibly take on the interval is 1. So this is less than or equal to, in fact, it's just less than. I'm trying to maximize this. The biggest x value could be is 1 because I'm just restricting myself to 0, 1. The biggest 1 over n could be is 1/2. X minus 1 over n. So that gives me 3/2 times x minus 1 over n. And I need this to be less than epsilon. And the way I can do that is I let x minus 1 over n be less than 2/3 epsilon. So notice that this works for any n. So for 1 over n, I can choose my delta to be equal to 2/3 epsilon. For 1/2, I can choose my delta equal 2/3 epsilon. 1/3, 2/3 epsilon. 1/4, 2/3 epsilon. 1/100, 2/3 epsilon. 1/1 trillionth, 2/3 epsilon. So maybe I should write this over in blue, very similarly. So I need, at 1 over n, I need delta to be equal to just 2/3 epsilon. So similarly, I can draw my little intervals. So this might be 2/3 epsilon. This might be 2/3 epsilon. That should be about the same size. 2/3 epsilon. 2/3 epsilon. And okay, so I need to do a little bit here. I can't go beyond 0, but you see, for most of the points, 2/3 epsilon is going to be sufficient. And the only reason why I'd ever need to go smaller is if I hit the end of the road over here. So for all the points, this delta works out just fine. Contrast that over here. Over here, at 1/2, you got to have a big interval that makes it work. And by the way, big interval means it's easier. It means, in some sense, it's more continuous because it's easier to be less than epsilon because more x values work. 1/3, you get smaller. 1/4, you get smaller. 1/100th, you're tiny. So the intervals, the delta intervals, get smaller and smaller and smaller here. And they're going to keep on getting smaller the closer you get to 0, as you can see from this term right here. Right? As n gets bigger, 1 over 2n is going to go to 0, and epsilon over 2n squared is going to go to 0. So the deltas are getting really small. Whereas over here, yeah, just one thing works. And this is the difference between uniform continuity. This is uniformly continuous because at every point is basically the same amount of continuous. You need, for a given epsilon, delta can be the same size. Here is not uniformly continuous, but continuous. And this is the main difference between the two. Uniformly continuous, same delta works for everything. Not uniformly continuous, you need smaller and smaller deltas.